Welcome to another draft physics presentation. Yay. Alright, so drag is the subject again, and so I've been doing some different figuring and thinking and trying to come up with some way to illustrate, even in metaphors. It's kind of a complex subject in the sense that these are all moving bits by the theory. And so when you're moving something through moving things, it gets more and more complicated to figure out the consequences. So I'll see what ideas I still like and which ones I don't, or I'll just do the new ones. So something I did consider, I'm still considering it. I don't like it, but I'm considering it, is spin. So I was thinking about objects circling each other or even rotating themselves. It's probably easier to illustrate with something that's circling another thing. And if you presume no friction in the orbit, that it can move around, and there's a force keeping it from rolling or doing something else that would cause friction or heat or dissipation of momentum or substance or whatever. You can sort of get the idea that once you have a rotation, when a incoming force comes in, and it's even across the whole surface, that what it's essentially going to do is cut this into two different paths. And one path it's going to reinforce velocity, and the other path it would suppress velocity. So in a sense you could think that nothing will really push down because there's a balancing force and with no friction. So essentially it either goes left or it goes right, the force. So the force comes in and it's converted to left or right in this idealization. And essentially you'll either make this thing go faster going this way by adding force, and as it comes around this corner it will be retarded in its progress by all the force that goes this way. And I would argue that it does that in equal proportions no matter how fast you go into the force. So no matter how much velocity you gain into it, it'll do the same thing. It'll accelerate this object down one side just as much as it decelerates it going around the other side. So conceptually I think that's solid, and I think it's sort of supported by observations in mediums when you're spinning objects. It's even like the old flying saucers were sort of relying on that. But you can sort of see it in a lot of circumstances where if the object is rotating, you just need to give it a tiny little hit and it'll go in a direction. It seems to have much less resistance to movement than something not spinning. So I think it's solid in that sense, and that this is theoretically correct. And so it might even have relevance to spinning planets and orbits and how they don't degrade because the object is spinning, and by spinning circumvents the resistance of what it's moving into. So anything it moves into, it essentially kills it with its spin. So like I said, I don't dislike it as a concept, but spinning electrons and protons and all of these things is back to the standard model, which I don't think is correct. And I also don't like it because it still doesn't explain how entering a new force comes in, how the new force has any more effect than any other force, in the sense that how would it stop motion, in a sense. I mean, you can think that you could stop motion by having a force that only hits, maybe a change of color would be appropriate. So if you had a force that only hits this side, and it doesn't hit this other side, well, then you can understand it's going to create more rotation. And likewise, one that comes from this side would suppress rotation or slow the spin down, so that in a sense a force could become more effective by slowing the rotation, which would make it possible, perhaps, for this force to have more effect. But that was one of the interesting questions when you start thinking about spin. Does it matter how fast it's spinning? I mean, if I spin it twice as fast, is it twice as effective? And there's no reason to think so. So it's, you know, it creates all kinds of curious questions that you can ask about how spin would function. So anyway, I like that it creates this ability to move through force with impunity, you know, without consequence, essentially, to some degree. And to most degrees that I can't find a real flaw, in the sense is as long as you can buy the idea that this little object isn't going to be, is only going to move, it'll never move this direction in a permanent way because it'll be pushed back. So it can only go this way, or left or right, essentially, and down and against the force here. So against the tide here, with the tide here. So go add velocity here, subtract velocity in the other direction. So anyway, it does explain the idea that something could move through a force, and its spin would, the orbiting thing, would almost stop. You could almost think at the top, and then start up again, and then stop, and then start up again. So it could be something that had no spin to start with, but as it gains velocity, it gains spin. Alright, it's one explanation. You know, possible, maybe. Yeah. Okay. Another way of thinking about it is this timing thing of a universe that has a clock speed, and that you could almost think that things are just jumping to a new spot in time. And you would kind of argue that the amount of force sitting here is going to be exactly the same as here, is exactly here, is exactly here, is exactly here. And if all you're jumping is little increments of time, so if you're jumping from these spots to this spot to this spot, you would have the same likelihood of encountering energy, because each one of these spots will encounter exactly the same amount of energy. So in a sense, you don't have any drag problem, because you're just jumping to new locations that have the same exact exposure to force. So my brain sort of likes that. When I started off a few years ago talking about clock speed and how the universe could have a clock speed, that is, it only does something on the clicks of the you know, when the pendulum swings right, things happen. Nothing happens left, things happen right. You know, however you want to understand it. It's just that the universe just updates at a Planck constant distance. So everything just moves a Planck constant distance, and that stuff doesn't count because everything's just changing its position. So the checkers, in the act of moving, they don't actually jump to another square. You just go from the checkers here to the checkers there, kind of thing. So that sort of makes logical sense. What I'm liking, the more I think about it, in terms of the speed issue, is the idea that, let's say this is an object and it's moving in this direction. Yeah, you can almost see that. Let me turn on this little flashlight, maybe this will help. Oh, the pen's in the way. Oh, yeah, that's a little better. What I thought about was what could possibly hit this object. Now, if it's standing still, then stuff out here could hit it, and stuff way out here could hit it, and stuff from all kinds of places would have a possibility of getting to it because it's not moving, so they have plenty of time to do their speed of light thing in this direction or whatever direction they have to go to. I mean, obviously to hit this, they'd have to hit this spot. But I just mean, if I imagine it moving very slowly, you can just imagine that this would just have to move a little bit. It would have to move in this direction and just a little bit in this direction to hit it. So anyway, so the point is that if it's standing still, the area of stuff that can hit it is this whole arc. You know, this anything can hit it from any one of these locations. But the faster it starts to go, I mean, the more it moves into that field, all of a sudden all those things that could hit it are no longer in the ballpark, and the only thing that can hit it is, you know, let's say stuff in this range. Anything outside of this range won't have enough time, like something here, it won't have enough time to get to do this distance and any other distance required. So you could sort of understand that it would always be kind of the distance would be the same line as this would be the distance of its speed. So these two lines would be the same distance theoretically. That would be the only way you could hit it. That would be the only realm of possibility would be in that arc. So my arc isn't perfectly drawn for this example. I mean, I should have used a shorter line here, and then it would have made more sense. But anyway, and you could imagine that at the speed of light, if this thing was moving the actual speed of light, and none of these bits could move any faster than the speed of light, then obviously anything that had to go, like say if this was going to end up here at the speed of light, the only way this could hit it would be going this way. It couldn't possibly hit it by having any direction this way. So this way would be impossible. So it couldn't have any angle. And the only possibility would be to directly shoot at it at its future position. So the point is that this arc just gets smaller. So when this thing's moving the speed of light, the only thing it can hit it coming from this direction, it has a component of its velocity in this direction. That is, it's coming from some angle, not straight line across. It has to be at some angle. The only thing that can hit it when it's going the speed of light is pretty much things coming straight at it. There's really no possibility of anything else because it can't have any component down. It has to have just component this way. Any component this way will make it fail to get there. So it can only hit things in a very tiny little wedge. So that's sort of intuitively making sense, in the sense that as you go faster, you're running into less to hit. Therefore, the two balance. Your velocity is essentially limiting what you can hit in proportion to your velocity, what can hit you. And especially this hitting thing has to be at the right. It's like maybe comparing it to, let's say, docking with a spaceship. If you were docking with another spaceship and the other spaceship is moving towards you and you're trying to dock, you can kind of understand that, you know, you're coming at an angle, let's say, well, this is pretty dicey. You know, this is going to be quite unlikely that you're going to be able to do that successfully unless you match this other thing's speed. I mean, the dock is going to be almost impossible. Where if you're coming up from behind, you have lots of latitude in terms of it'd be a lot easier to do because you both have a component of speed in the same direction, and so it's going to be much easier to match your pattern, your shape, your any requirement that you have to go through something in a specific way will be met if you're coming from behind and something has a component of your speed. So if you're going 100 miles an hour and it's going 50, it's going to be a lot easier to bump into its bumper than if you're coming straight at it. You're not going to be able to do the bumping thing. You're going to do the crashing thing. So, and I'd say the inverse, it creates the inverse from behind, in the sense that once this gains speed that this force has. So this stuff's moving the speed of light, remember, and this thing's moving much less than the speed of light. Don't know how to, I guess it's less than c, and this is greater than c. Well, it is c, equal to c. So you always have to understand that this force coming from behind is still going to exist. The fish swimming from behind are still going faster than this object, because this object is a collection of fish, a school of fish, and the school of fish never goes as fast as the single fish. And so, in a sense, while this arc is getting smaller, this arc is getting larger. It's not kind of. Because things further away can match the speed now, where they couldn't before because they were going too fast, they would miss it. Now they'll hit it because it's moving the same speed as they are. So now it's possible to have this angle and still hit it because it's going to be in the forward position. It's going to have a portion of your speed, and that's going to make it possible for those things to equal out. So I'm liking this. Obviously it needs more work, but I mean, in theory it sort of makes sense. So as the field gets narrower in this direction, it gets wider in this direction, because objects can hit you theoretically. But see, the test is also, if you think about it, say if this thing was going the speed of light, where only these things could hit here, the same is true here in the sense that nothing can hit from behind from any position, because nothing could catch up to it. So then you have the problem of it's moving away too fast and you can't catch up to it. So it does balance in some ways in that respect. So you can't really use the backward energy will be greater argument, because I don't think it would be. But clearly this narrowing of the forward potential, I think, is significant. So another way to look at it, there's the only distinction between, so you still have to understand that force still has to be able to turn something or stop something. So the thing you're trying to find is what's the distinction between a force coming from some other direction, from some other source that's going to hit the thing and stop it from moving, and the force created by the velocity. The acceleration essentially creates an equal and opposite force coming right at you in any particle theory of momentum. And but the key is there's a subtle difference. So a way of illustrating it is sort of like by just changing the frequency of lines, and just say, these lines represent what happens to the force when you're moving into it. So when you're moving into a force, the lines go from nice and wide into a higher, it's like you're moving into a higher frequency essentially, and that's all you're really doing. You're just changing the amount of, you're changing when you'll get hit in an amount of time. You're not changing how much you're going to get hit really. You're just changing how much you're going to get hit over time. That's not exactly true, but whatever. So, and this doesn't look as, I mean, I guess I should have added, I should have made it a little more dramatic a difference. But anyway, so when I thought about that, I was thinking about sailing, because sailors move into a wind that's coming at them. So they have a wind coming at them, and they actually are able to, tack and create force, torque against their boat. So the wind's trying to turn the boat, they don't let it turn the boat, and by doing that, they turn the force into a force in the direction of their choosing. And so as long as they just keep going back and forth, they can get forward progress against a wind against them. So everything says the boat has to go that way, but because they're able to use the water and the position of their boat as torque, something to push against, trying to get the wind to force the boat to turn, and they're doing the opposite thing. They're putting a rudder in the water that says, I ain't going that way, and they're doing everything they can to keep the boat from turning. And that way they can, make forward progress against a wind that's decidedly against them. So as I pointed out in the previous illustrations, that if you can create a force that is trapped in these diagonal directions, essentially you can create this forward push of the wall, so to speak, up, as long as this boat has torque, as long as it can't be pushed down. And as I have argued, and as long as this can't be pushed out. So the only thing you really have to consider as a possibility with this model is that there's forces holding the atoms on the surface. Let's say this was the well, I could probably draw it. I should probably make a bigger drawing. Sorry, rip a piece of paper. A little noisy. So again, I'm not. This isn't my favorite concept, but I don't hate it. Like I said, like I said, there's 3 or 4 viable ways of understanding how you can get around this, how you can trick this force problem. Alright, so there's 3 things, 2 electrons and a proton, and just pretend this is a 90-degree angle, and the idea would be is that force travels in these 2 directions, back and forth, these 2 paths, and it turns in the proton. So the proton is the torque. This is essentially the tack, and because these electrons are tied to other elements in the atom, they can't be pushed out this way. So they'll always convert any force that has an element in this direction into a full element in this direction. So that's the way it will move, is this way. So when it gets hit, it moves this way. So when the force comes in, hits it, it moves it up. And at the same time, this proton is, say, attached to the same surface as this is, so it gets moved up. So you could argue that that's the torque that it's working against. The other argument is that this is a full a full bit of energy in this direction. Okay, 100%, we'll call it, of a bit of energy. A speed of light of a photon, the momentum of the speed of light, the momentum of a photon, essentially this way. It's the whole momentum. Where the force that comes down here and goes through the intersection, which the intersection is just converting this into this, this direction into this direction. And the catch would be is that it would leave a residue in this direction, momentum push on this in this direction. Now the key is this direction isn't this direction, so it's only half of it in essentially. So it doesn't have any component all the way down, so this doesn't equal that. So this only really equals a 50% in this direction. So it got 100% this way and only 50% this way, and then it goes 100% this way, and then only 50% this way, and just keeps doing that. So it's so you can either make this rigid in the sense that you can tie it to this surface, and that way it has to move when this moves 1 photon worth up this way. This one also has to go with it because of all the forces connecting everything. Or if you loosen it, you can recognize that the force this way is a full momentum, and the force going this way is only a half. So you got a half going this way and a full going this way, which means this would have motion in this direction overall. Alright, so I think those are the basic ones. I mean, I had some other ideas. I mean, it's, you know, there's all kinds of ways of trying to figure out how, like, again, the distinction you're trying to make is between force that's coming in straight this way, because that's really what it's about, right? And when you're moving in a direction, what you're doing is creating force that's all coming at you in a certain direction, essentially. And that's the big distinction between, say, you having elements of momentum in all these directions. You could have elements of momentum in many directions, and they all create a net movement in this direction. So that's your net movement, but your real movement is in all these directions. So when you have velocity into the field, the truth is, though, is the real meaningful force is all going to be in this direction. And so theoretically, you could say that if this didn't count, I mean, if if there was no real center, you know, then you could theoretically say that this force becomes moot because it just travels right through something. So you could almost think that the something would just be two halves, and because the force is hitting this way, it's moot, so to speak, because it can only hit perpendicular to its motion. So it can either hit this way or head on, but it can't do this angle thing when it's moving. So, you know, you just create rules for that. But that requires a more complex mechanism, but there's no rule against it. I mean, you know, the universe can have, you know, Rube Goldbergian elements even in the foundational structure. I mean, it can be bowling ball and bowling pins, but, you know, bowling balls and bowling pins can be doing lots of different things to cause and effect. So I like the simplicity of this. I certainly like the idea of recognizing that when you're I have this vector thing. I like the idea that the faster you go, the less stuff can possibly hit you, because no matter where your location is, you've eliminated all this stuff from being in the field that can hit you, and that's sort of, that one feels good. But whether it's right or not, I don't know. And the spin thing is obviously quite interesting. So it's all stuff that still needs more thought. And I really hate investing all this time in, you know, one subject, but it is nagging. I mean, it's still sitting there saying it needs an answer. So I'm compelled to think about it. But I'm also recognizing that it probably has to do with, again, you know, where I was drawing the protons and the electrons. This is probably what needs to be done. Is you need to understand how atoms are configured to be able to understand how the different elements in the atom is going to react. And I think it is curious. You know, I've mentioned that it sort of seems like, anyway, it seems like, maybe it's not true, that electrons aren't terribly interested in gravity, that it doesn't have much effect, because there's very little evidence that if I put two plates up, you know, that I'm going to get a spark at the bottom more often than I'll get a spark at the top. And you would just think intuitively that if electrons are a little bit mobile, it wouldn't take much extra force to force more of them to collect at the bottom than would collect at the top. Now, whether that matters to overall charge, maybe it doesn't. You know, because the protons would react to the extra amount of electrons on the other surface, and so maybe there are reasons why it is happening, but it isn't creating any effect. I still think it would have to. So anyway, and the same sort of goes for the protons, which would say, you know, they would sort of lump at the bottom, tend to, you know, if they had any kind of, if the matter was at all loose, you'd think even in the atmosphere there'd be a huge amount of charge difference. Now, it's obviously there is some in the sense that lightning is created. But that's more about scraping electrons off of things through movement. So I'm not too sure. That just has more to do with molecules being forced to hit each other. Then maybe it has anything to do with any atmospheric condition where there's more of something somewhere than somewhere else. And I'm just not too sure which ones, off the top of my head. I don't know. Do clouds get positive charge on the bottom and negative charge on the top? So again, I mean, it's, wouldn't there be a tendency for gravity to have a preference? And I don't know. It's, you could spend, a lifetime just studying, one little piece of all of this physics. But anyway, enough of a video. So just chiming in that I'm still working on it. I think there are solutions here. So for the people who say it just can't be done, I guess I would just argue that, well, sailboats do it. If sailboats can do it, probably matter bits can do it. But anyway, enough of the video for now. Till the next time and such.